The Monty Hall problem, a battle between imagination and reality. Upon deeper reflection on the Monty Hall problem, one will realize that the debate surrounding this problem is essentially a battle between imagination and reality. The reason why the traditional answer to the three-door problem is widely accepted and firmly believed by many lies in the fact that the so-called simulation algorithm confirms the predicted results. That is, switching doors can increase the chances of winning to 2/3, doubling the odds compared to not switching doors. Once the results of the algorithm are repeatedly confirmed, this answer is locked in the unquestionable realm of authority by the public. The majority of people will no longer entertain any questioning analysis. For the skeptical camp, the key battle is to point out the fundamental errors in the traditional algorithmic model. The core of analyzing the Monty Hall problem lies in the information provided by the host opening a door. This forms the logical basis for analyzing the probability distribution of the three doors. It is evident that the decisive proposition provided by this information is that in each round of the game, the possibility of a car behind one door has already been eliminated. This also becomes a prerequisite for the second choice. There are only two possible arrangements of prizes that may exist. However, in the traditional algorithmic model, what is actually generated is a random sequence containing all possible permutations and combinations. The final results obtained from the statistics do not truly simulate the arrangement of a single game, even though these data indeed come from the statistics of each simulation. The reason for this is that such simulations fail to undergo necessary inductive processing of the statistical data, especially concerning the door chosen by the host to open. Although from a gaming perspective it merely represents no prize, in terms of probability analysis, the two doors actually represent two different paths of probability distribution. What differentiates these paths are the two goats that replace the grand prize. Let's assume one goat is goat A and the other is goat B. When processing simulated data, the data sequences formed by the appearances of these two goats are crucial in analyzing the probabilities of the Monty Hall problem. Now, let's use a set of simulated random sequences of 30 games to illustrate. The first set of data pertains to the induction of probability variables. The first column of data summarizes the results of the guest's initial choices. The second column shows the sequence of goat A appearances, with the positions occupied by the prize indicating when goat A was chosen by the guest initially. The third column represents the sequence of goat B appearances. While this set of data is not the most original random data, it is entirely equivalent to the original sequence, having undergone classification processing. The second and third sets of data are the results of sorting based on the sequences of goat A and goat B, respectively. It is now evident that in the highlighted areas of the two sets of data, all instances involve the appearances of goat A and goat B. This signifies that the corresponding doors were opened by the host, indicating that there is no possibility of a prize behind the open doors in this region. Thus, this region is the effective data area when considering the appearances of goat A or goat B. The areas highlighted in gray represent redundant information overlaid by naturally generated random sequences and should not be considered. Why is it necessary to divide the original random sequence into two different forms expressing different states to make a correct comparison? This is because merging the states of the two remaining doors and comparing them to the initial choice would lead to a logical paradox. That is, two mutually exclusive probability states are combined into a single comparison object, rendering the comparison meaningless as we cannot clearly discern which state is being compared. If this reasoning is difficult to grasp, there is a more straightforward principle of inference. If a reasoning is correct, then it must be universally applicable within its domain. From the intuitive pattern of the simulated data, it is clear that in any single-state sequence distribution area, both switching and not switching doors have a 50% chance of winning. It is only when the results of the gray area are included that switching doors leads to a 2/3 chance of winning. This clearly indicates that the doubling of the chances by switching doors can only be achieved under specific data combination conditions. However, these combinations are actually invalid. Any person with common sense cannot deny that the correct answer to the Monty Hall problem should apply to any arrangement of prize placements. Even if our simulated sequence only represents one particular state, it should still yield the results indicated by the answer. Otherwise, either the theory is wrong, the algorithmic model is wrong, or both could be incorrect.